In this video, you'll be introduced to character tables and the concept of a representation of a group. Consider the C2V point group, which contains 4 different symmetry elements: the identity element, a C2 rotational axis, and 2 mirror planes that are 90 degrees from one another. An example of a molecule that falls within the C2V point group is methylene chloride. One way in which we can depict the different representations and their relationship to one another is through a group multiplication table, which tells you what the product of any two operations are. So for example, the C2Z times the sigma xz will give you the sigma yz operation. For those who are curious on how to construct these different multiplication tables, there's a video that I've made that goes through their construction and also how to multiply different symmetry operations together. I've included a link to that video in the description. Another way in which you can depict the relationship between the symmetry elements in the C2V point group is by using a character table. A character table contains a huge amount of different information concerning a point group. For those who are interested, subsequent videos will go through the steps involved in constructing a character table. This video will just walk you through the different information that's contained in a character table. In the upper left-hand corner, there's this h equals 4 term. The h is the order of the group. This is just the number of operations that are contained in that particular point group. For the C2V point group, that's 4, the E, the C2, and the 2 sigmas. In the middle, we have these headings that contain the different symmetry operations of the point group grouped into classes. A class are just operations that are related to each other through a similarity transform. In the case of C2V, each operation is in its own class. Once again, we'll be going into the concept of classes in a future video. Each row contains an irreducible representation of the C2V point group. In a few minutes, we'll define what an irreducible representation is. Each irreducible representation is labeled with a Mulliken symbol that tells us something about the symmetry of that irreducible representation. The irreducible representations are specified using characters, which are symbolized with the Greek letter chi. When we go through and define an irreducible representation, we'll also be defining the concept of a character. In the column over from the characters, we have some information about how the linear and rotational functions transform under C2V symmetry. These will be defined towards the end of this video. Finally, the last column depicts how the square and binary product functions transform under C2V symmetry. Once again, we'll be going through and defining these towards the end of the video. But first, let's go through and define the concepts of a representation of a group as well as characters. A character is the trace of a square matrix that's used to represent different elements of a group in such a way that they satisfy the multiplication table of that group. These characters can be positive and negative integers, imaginary numbers, trig functions, and sometimes matrices. If we collect characters for each symmetry element, what we have is a representation of a group, which is abbreviated with the Greek letter gamma. So a representation for the C2V point group would contain a character for E, a character for the C2 rotation along Z, a character for the mirror plane corresponding to the XZ plane, and a character for the mirror plane corresponding to the YZ plane. A representation that satisfies the group multiplication table is this one here, where all the characters equal 1. We can take a look at the group multiplication table, which just relates the product of any 2 elements to give that third element. If we substitute the characters into this multiplication table, we have something like this. And just going through, multiplying the row position by the column position, we can see that 1 times 1 for the E gives us 1. And we can go through and fill this out for the entire character table. What we find is that this satisfies the multiplication table. So let's take a look at the C2 and a mirror plane. So those two positions in the group multiplication table yields this sigma mirror plane. If we look over at the multiplication table for that gamma 1 representation, we find that those two positions each have characters related to 1, and then the resulting character is 1. This satisfies group multiplication. No matter how we multiply these characters, we get the same character back that corresponds to the original representation. So 1, 1, 1 satisfies the group multiplication table. It's a valid representation of the C2V point group. Another valid representation of the C2V point group would be if we kept the character for E and C2 1 and the characters for the mirror planes as -1. We can go through, substitute those into the group multiplication table, go through and multiply it through, and we find that it satisfies the group multiplication table. For example, if we look at all of our mirror planes along the xz plane elements, those correspond to a value of -1. And in the character table where we substituted in the characters, what we have is this. So this satisfies group multiplication. This applies for every single element in the C2V point group. A representation that does not satisfy the group multiplication table would be this one, where the character for E is 1 and all the other characters are -1. We can go through and generate a multiplication table using these characters, and we have this. So in this character table, there are places where, for example, the character for the C2 along the z-axis corresponds, but there's also places where it doesn't, highlighted in red. Same goes for our two mirror planes, so the one along the xz plane and the other along the yz plane. There are places where you get the character out that's correct, but there's also places where that -1 has been changed into a 1. Because of these different operations, this representation does not satisfy the group multiplication table. Therefore, this is not a valid representation for the C2V point group. Even though not every single representation will be a valid representation for the C2V point group, it turns out that there's an infinite number of valid representations for every group. Of that infinite set of valid representations, for the C2V point group, there's only 4 representations that we call irreducible representations of the C2V point group. And I have those irreducible representations highlighted over on the left. Every single other representation of the C2V point group is a composite of those irreducible representations. We call all those other representations reducible representations because they can be reduced into the 4 irreducible representations of the C2V point group. An example of a reducible representation would be this one, the reducible representation equal to 2, 0, -2, 0, which is a composite of the second and the fourth representation of the group. The characters that comprise the representation tell us something about the symmetry of that irreducible representation. For this, if a character has a positive 1 value, then that tells us that it's symmetric with respect to that operation. And if it has a -1 value, it tells us that it's anti-symmetric with respect to that operation. Because every character is symmetric with respect to that particular operation in that first row, that gamma 1 representation is what we would call the totally symmetric representation of the group. The totally symmetric representation has a character equal 1 for every single operation, and every single point group has a totally symmetric representation. If we look at the column corresponding to the identity element, we see that in every case is equal to 1. Every valid representation of the group will have a positive value associated with the identity representation, with the number indicating what the dimensionality of that representation happens to be. Remember, these characters are matrix traces, so a matrix trace of 1 for an identity element can only result from a one-dimensional matrix, so a scalar. Therefore, the dimensionality of all 4 of these representations are one-dimensional representations. If E happened to be 2, it would be a 2-dimensional representation. It would be the trace of a 2x2 matrix. If it was 3, it would be a 3-dimensional representation. It's the trace of a 3x3 matrix. To start to get an idea of how we can use these representations for chemical problems, we're going to look at two different orbitals and ask ourselves how these two orbitals transform under C2v symmetry. We're going to look at a pz orbital and a px orbital. With the pz orbital, you do an E transformation and it stays the same. We give that a character of a 1. You do a C2z and it stays the same. It has a character of a 1. You do a sigma xz, it stays the same. We give that a character of 1. You do a sigma yz, it stays the same. We give that a character of 1 also. So with respect to each one of these operations, the orbital is symmetric with respect to those operations. Those 4 characters correspond to a representation of the C2v point group. In this case, it's that first totally symmetric representation, the gamma 1. In the case of the px orbital, we go through, we do an E, it stays the same, it gets a character of a 1. We do that C2 rotation along the z-axis, and the two lobes of the px orbital change. It is anti-symmetric with respect to that operation. It gets a character of a -1. The mirror plane that contains the xz plane, it's symmetric with respect to that operation, but it's anti-symmetric with respect to the other operation. The characters for this are 1, -1, 1, -1. So the px orbital transforms as gamma 3 under C2v symmetry. Calling these representations gamma 1, 2, and 3 is a way that you can notate the different representations, but it's not the most informative way. Therefore, a method has been developed that's called Mulliken notation. We use Mulliken symbols to characterize the different representations for point groups. We're going to go through and assign Mulliken symbols to these different representations, but first we're going to go through the rules for assigning Mulliken symbols. And first we're going to go through the rules for nonlinear groups. So all groups with the exception of the D infinity H and the C infinity V. The first thing you do is you look at the dimensionality of the group, so what that E column corresponds to. If it's a 1D group, then you give that a letter of an A or a B. And what you do is you look at the highest order CN axis to distinguish between an A and a B. If it's symmetric with respect to that highest order CN axis, you give it an A. If it's anti-symmetric, you give it a B. If that E happens to correspond to a two-dimensional representation, so E equals 2, then you give it a letter of an E. And if E equals 3, meaning you have a three-dimensional representation, then you give it the letter T. The next thing that you do is you look at your inversion center, if your group happens to have an inversion center. If it's symmetric with respect to that inversion center, then the representation gets a subscript of G for gerade or even. If it's anti-symmetric, then it gets a subscript of a U for ungerade or uneven. So moving along, we can look at a non-principal CN axis, so with perpendicular C2 axis or a mirror plane. And you look at the first one that's listed in the character table. If you're symmetric with respect to that axis or mirror plane, you give it a subscript of a 1. If you're anti-symmetric, you give it a subscript of a 2. Most of the time, that's enough to distinguish between different representations. Sometimes you need to use a subscript of a 3 by looking at other lower order axes of rotation or mirror planes. Finally, you can distinguish between different representations by using primes and double primes by looking at the horizontal mirror plane. If you're symmetric with respect to a horizontal mirror plane, you use a prime. If you're anti-symmetric, you use a double prime. When you're going through and you're assigning Mulliken symbols to irreducible representation, you only distinguish between them until you've distinguished between every single representation in a group. So once you can identify each representation with a unique Mulliken symbol, you stop. You don't go and list additional information concerning that particular Mulliken. As I said, these are the rules that you use for nonlinear groups. If you happen to have a linear group, then we use Greek letters as opposed to Roman letters. So for linear groups, a 1D representation will have a capital sigma. A two-dimensional representation will have a capital pi, delta, or phi. If you have a subscript of a 1, you give a superscript of a plus. If you have a subscript of a 2, you give a superscript of a negative. And you retain that inversion center GU labeling system. So let's go through and assign Mulliken symbols for the C2V point group. This is a non-linear group, so we use the rules that are to the left. So first, going through, looking and seeing what our representations are. They're all 1D representations, so we have to look at the highest order rotational axis. If it's symmetric, we give it an A. If it's anti-symmetric, we give it a B. So the first two get an A because those have characters of 1. The last two get a B because those have characters of -1. Next, we looked at the inversion center. There is no inversion center in this group, so we skip number 2 and move on to 3, where we look at the non-principal CN or the mirror plane. So we're going to look at the mirror plane. There is no perpendicular C2. That's sigma xz. If it's symmetric, we give a subscript of a 1. If it's anti-symmetric, we give a subscript of a 2. So going through, looking at that mirror plane, symmetric, 1. So we have the A1 for the first representation, the B1 for the third representation, anti-symmetric, 2, the A2 for the second representation, and the B2 for the fourth representation. Going through, there is no mirror plane, but even if there was, we wouldn't need to use it because each Mulliken symbol is unique from every other Mulliken symbol in this group. We've distinguished between all 4 different representations with a unique identifier. So continuing on, we're now going to look at the linear transformations. These linear transformations tell you how a vector oriented along the z, the x, and the y direction transform upon the different operations in the group. So going through, for the z vector, the C2z keeps it in the same place, so it gets a character of 1. For the x vector, it changes position, so it inverts. It's anti-symmetric with respect to that operation. It gets a -1. For the y, the same thing happens. It gets a -1. For our mirror planes, our horizontal or our vertical mirror plane in the xz plane, we have a character of 1 for z. It doesn't change its direction. Same for the x. It doesn't change its direction. But for the y, it will change its direction. The direction of that vector swaps, so it's anti-symmetric with respect to that operation. Looking at the second mirror plane, the sigma yz, the z vector stays the same. The x vector inverts, but the y vector stays the same. We can look and see which irreducible representations these transform as. The z vector transforms as a1, the x vector transforms as b1, and the y vector transforms as b2. Relating this back to chemistry, something to note is that your p orbitals will transform in the same way that your z, x, and y vectors transform under that particular group. So the py orbital, for example, transforms as b2 under C2v symmetry. The rotational vectors tell you how a rotational vector transforms. What I have depicted here are the rotational vectors along z, along the x-axis, and along the y-axis. So these are rotations that obey the right-hand rule. If you rotate the rz vector, it stays the same. You're just rotating in the same direction as the rotation, but both the rx and the ry invert. If we do a mirror plane reflection, we invert the direction in which that rz vector is rotating. It was going counterclockwise, it's now going clockwise. Same thing for the sigma xz on the rx vector. However, the ry vector keeps going in the same direction. If we look at the sigma yz, the rz vector also changes its direction. The rx does not, but the ry does. So if we look and see how these transform, the RZ vector transforms as A2, the RX vector transforms as B2, and the RY vector transforms as B1. To finish up, we're going to look and see how the square and binary product functions transform. So the xz function would be the x vector times the z vector. Another way of stating this is it would be the b1 representation times the a1 representation, because that's how the x and z vector transform under C2v symmetry. So we would be doing the dot product of these, and when we do that, what we get is the xz vector that transforms as b1. So b1 times a1 equals b1. For the xy, we look and see how the x vector transforms and the y vector transforms. So those transform as b1 and b2. You take the product of those two vectors and you get a2. So the xy binary product transforms as a2 under C2v symmetry. You can do this for all combinations and fill out that square and binary product function column. Once again, relating this back to chemistry, this is how your d orbitals transform. So if we look at the dxz and the dyz and perform the symmetry operations of the group, we find that the dxz transforms as b1 symmetry, and the dyz, or xy, transforms as a2 symmetry. So the d orbitals transform as the square and binary functions of the group. Just for your information, an s orbital will always transform as the totally symmetric representation of the group. So under C2v symmetry, an s orbital transforms as the a1 representation. For those who are interested, we're going to go a little bit more deeper into character tables in some subsequent videos, and we're going to talk about how to construct these character tables. And we're going to start with the concept of a class. So what is the class of a group, and how do you determine which elements belong to which classes in a group?